Hello everyone. Today we are going to explain you about the experiment titled RTD studies in PFR. The objective of this experiment is to study the behavior of RTD in the PFR. The aim of this experiment is number 1 to plot the RTD curve for PFR using pulse tracer. Number 2 to determine the dispersion number. The apparatus required for this experiment: 10 ml of measuring cylinders for 15 different readings. In this we will collect the samples for the experiment. Second, 250 ml of conical flask. In this we will titrate the solution which is obtained. After that we will use the syringe of 12 ml. This syringe is used for injecting the tracer into the PFR. Next, phenolphthalein indicator. This is an indicator used in titration. After that, this is buvette. In this buvette, we will fill the NaOH for the titration.
So now the theory. What exactly is residence time distribution or RTD? Simply put, RTD is a way to describe how long different molecules or fluid elements actually spend inside the reactor. Imagine you are standing at the exit of a chemical reactor with a stopwatch, trying to see how much time each molecule spent inside. RTD is a mathematical tool that helps us analyze that information. Understanding RTD is crucial because in any chemical reaction, the amount of time the reactant spends inside the reactor influences how much they react, which in turn affects the overall yield, selectivity, and the efficiency of the process. Now, in an ideal world, we would have perfect control over how long every single molecule stay inside the reactor. But as we will see, reality is something different. So now the concept of PFR or the plug flow reactor. Uh, PFR or plug flow reactor. Imagine you have a long straight pipe where a fluid flows through in a perfectly organized manner. In an ideal PFR, the flow pattern is such that all fluid elements move through the reactor in a perfectly line fashion, like a series of piston or a train of fluid slugs. There's no backmixing or no turbulence that would cause fluid elements to interact with one another. They just flow straight through. Think of it like a highway where every car enters, travels at the same speed and exits as at the same time. This is what I mean by plug flow. Now let's introduce an important term here: space-time, denoted by tau. The space-time is theoretical amount of time it takes for fluid element to pass through the entire length of the reactor, and mathematically it's defined as tau equals to V by Q. Here, the V is the volume of the reactor and Q is the volumetric flow rate of the fluid. For an ideal PFR, this means that every molecule spent exactly tau units of time in the reactor. Now, the deviations from the ideal plug flow behavior. Uh, Ideal plug flow rarely happens in actual industrial reactors. In practice, fluid flow can disrupted by many things like axial dispersion, channeling, or even irregularities in the reactor design. This means that some fluid elements may take a shortcut and exit the reactor sooner, while others might take longer path and get stuck inside for a bit more of time. So inside of every molecule spending exactly the same amount of time, we get a distribution of residence time. Hence, residence time distribution or RTD. Now, understanding RTD through tracer experiments. To measure the RTD in real reactor, engineers used something called a tracer experiment. Now, let's break down how this works. So, let's imagine if you are injecting a small amount of tracer substance like a dye or a non-reactive chemical into the inlet of your reactor. This tracer acts as a marker, allowing us to track how it moves through the reactor. Then you measure the concentration of this tracer as it exits the outlet over time. So now let's visualize this. For an ideal PFR, if you inject a pulse of tracer at the time 0, you would detect a sharp spike exactly at the time tau at the outlet, because all the fluid elements spend the same amount of time inside the reactor. But for the real reactor, the sharp spike turns into a broader curve. The curve tells us that some molecule exited early while others took a bit longer. Now let's analyze the RTD curve, the function of E of t. Now to quantify the spread of residence time, we use a function called E of t, which is the RTD function. It's essentially a probability distribution that tells us how likely it is for fluid element to exit the reactor at a given time t. The formula for E of t in case of pulse input is E of t equals to C of t upon integration 0 to infinity C of t dt. Here, C of t represents the concentration of the tracer at the outlet at time t. The denominator normalizes the entire curve so that the total area under the RTD curve is always equal to 1. This normalization ensures that the RTD curve reflects the probability distribution of residence time. In practical terms, E of t helps us to identify whether we are getting closer to that ideal plug flow behavior, or if there are significant deviations due to issues like dead zone or backmixing. So now let's discuss the practical applications of RTD analysis. So why we do this much effort to find RTD? So understanding RTD is incredibly useful for optimizing reactor performance. For example, number one, diagnosing flow issues. By analyzing the RTD curve, engineers can detect problems like dead zones, areas where fluid stagnates, or channeling where the fluid take a shortcut through the reactor. Improving reactor efficiency. So if you know that the reactor is deviating significantly from the plug flow, you can redesign the system to minimize these deviations, thereby increasing conversion rates and efficiency. Scaling up processes. When scaling up a process from a lab scale to an industry scale, understanding RTD helps ensure that the scaled up reactor will behave similar to smaller one. This can save a lot of time and resources during the scale process. So now let's discuss the RTD in non-ideal reactor and comparison with other reactor types. Before we wrap up, let's briefly compare RTD in PFR with other reactors like continuous stirred tank reactor or CSTRs. In CSTR, the fluid inside is perfectly mixed, which means that the molecule can exit at any time. The RTD curve for CSTR is an exponential decay, indicating that some fluid element exit immediately while others stay much longer. In contrast, an ideal PFR has very sharp RTD curve, while real world PFRs will have something in between, a narrower curve than a CSTR, but not a perfect spike. So now let's head towards the conclusion. To sum up, residence time distribution is a powerful tool that helps us to understand how fluid moves through the reactor. For plug flow reactor, the goal is to keep the flow as close to ideal plug flow as possible, which maximizes efficiency. However, the real reactors are not perfect, and RTD analysis helps us identify and fix the deviations to improve performance.
Now let me explain you the experimental setup of this experiment. First of all, we have our main storage tank. In this we store the liquid through of which we will perform the experiment. The liquid is stored here, and behind this we have a electric pump which is supplied by the main power supply. This when we turn on this power supply, the electric pump pumps the liquid from the storage tank to the overhead tank. This overhead tank stores the liquid, and when it is filled, we turn on the feed knob. The feed knob the liquid flows through the feed knob and is connected to the rotameter valve. This rotameter is used to control the flow rate of the liquid in the PFR. So this is the rotameter flow rate adjusting knob through which we can adjust the different flow rates which are written on this rotameter. The outlet of this rotameter is connected to the inlet of PFR. We have a long coil PFR which has an inlet through which the liquid is supplied and an outlet through which the liquid flows out, and the sample knob through which we take our samples. This has a tracer inlet through which we give our inlets. In this experiment we are going to give a step input, so we will be using a syringe through which we will give a step input. And further we have a drain knob down there which is used to drain the experiment after the experiment is complete. Now let us dive into the experimental procedure of this experiment. Firstly, let me tell you the opening instruction of this experiment. We will make sure the main power supply is off. Then we will make sure that the drain knob is on off condition so that no liquid flowing should be drained. Then we will make sure the rotameter is on off position or at the zero flow rate condition. Now for the first reading, we will turn on the main supply and we will notice that the electric pump will start flowing, will start pumping the liquid from the storage tank to the overhead tank, and then we will wait for a while for the storage tank to get filled. Meanwhile, let us set up the tracer input for this experiment. In this experiment, we are going to use the tracer as glacial acetic acid, which is an inert tracer for this experiment. We will be providing the input through this syringe. In this syringe, we will take 10 ml of our tracer and we will put this syringe in the tracer inlet of our experiment. Now we will notice that the liquid has started flowing from the overhead tank to the rotameter valve. We will make sure that there are no air packets in this pipe so that smooth recirculation is maintained. Then for our first reading, we would like to maintain the flow rate at 10 liter per hour. So we will turn on our rotameter valve and set it up to 10 liter per hour. After the flow rate, we will set the flow rate, the liquid will start flowing from the rotameter to the PFR inlet. The PFR inlet liquid will start flowing from the tubes and we will wait for the liquid to come out from the outlet. As soon as the liquid comes out from the outlet, we will wait for the reactor to attain its steady state. In this experiment, we will wait for around 8 minutes for the steady state to attain. While waiting for the reactor to attain the steady state, we will set up our tubes in which we will take our 15 samples. Here are 15 cylindrical vessel of 10 ml each. After that, we will fill our burette with NaOH against which we will titrate our further readings. After the steady state is attained, we will now give the step input through the tracer. Now we need to make sure that we give all the input at once as it is a step input. So we will give the step input at once and then soon we will start the timer. In this experiment, we have to take 15 readings at an interval of 1 minute. After 1 minute, we will take our first sample. Now, like this, we will take 15 sample readings for this experiment at an interval of 1 minute. After the 15 readings are done, we will turn off our flow rate to 0 and we will turn on our drain valve of the reactor and let the PFR drain. While the PFR is being drained, we will perform our titration. Now, as we have taken the 15 sample readings, now we will perform the titration. For our first titration, we will take the sample of 10 ml and we will put in our conical flask. Here we have a 250 ml conical flask. We will put our sample readings in this. After putting the sample readings, we will use the phenolphthalein as an indicator. As we have a acidic sample, as the tracer is acidic, so we will use a phenolphthalein indication for the acid base titration. We will put 2 to 3 drops of phenolphthalein in this conical flask. We will fill our burette with the NaOH solution, which is having a normality of n by 10. Now we will take our conical flask and we will titrate it against the NaOH. We will slowly start titrating, and then after a few ml of NaOH is dropped into the conical flask, we will notice a color change is being observed. After the pink color is attained, we will stop our titration. That is the end point of our titration. The end point of our titration, we will notice the amount of NaOH which is being used in the titration. So we will notice the reading and note down in our observation table. We will repeat our experiment for all the 15 readings, all the 15 samples of titration. As we have performed our first reading and we have drained our reactor, we will set up a reactor for the second reading. So we will turn off our drain knob from the below, and we will start our flow rate for the second reading. For the second reading, we will use the 20 lph flow rate. We will set up the rotameter knob to 20 lph. We will notice that liquid has started flowing in the reactor. When the liquid will come out from the outlet, we will again wait for the steady state to attain. For this flow rate, we will wait approximately around for 6 minutes. Now we will again set up the tracer input for the second reading. We will take the 10 ml acetic acid as a tracer and put it in the tracer inlet. After the steady state is attained, we will put a step input in the experiment and start our timer. For the second reading, we will take 10 readings at an interval of 1 minute. After all the 10 samples were taken, we will turn off our flow rate to 0 and we will drain our reactor. Then we will turn off our main power supply as the experiment is complete, and we will drain our storage tank. Again, for the second samples, we will take each of the sample and titrate it against the n by 10 normality of NaOH. We will repeat the procedure. We will take 10 ml of sample in the conical flask. We will put 2 to 3 drops of indicator and we will titrate it against the NaOH till the pink color is achieved. That will be our endpoint, and we will note the readings. In this way, we have completed the performance of our experiment. We have all the sample readings for the 10 liter per hour and 20 liter per hour readings. Now we will further move on to the calculations.
Hello everyone, my name is Kushal Patle. So moving to the next part, that is observations and calculations. So from the experiment procedure, we get the value of volume of NaOH, that is V, and this is time. Uh, from these two values, we will be getting some other terms also. So first of all, this C, what is C? This C is basically concentration of glacial acetic acid, which exists from PFR. So for the calculation of C, how can we get the C? So for this, here is the calculation. This is we will use this formula N1V1 equals to N2V2. This N1V1 represent equivalent of NaOH and N2V2 for glacial acetic acid. And our main motto is to find N2 from here, and N1 will be fixed, that is normality of NaOH, and V1 will be changing. We will take V1 as this values V, and this V2 will be fixed, that is the volume we took during the procedure of glacial acetic acid, that is 10 ml. So from here we can get N2, and N2 is basically same as C, and N2 is equals to C. This is because the N factor is 1 for glacial acetic acid, and for all the readings similarly we can calculate the value of C, and we will take summation of this C. So after this, moving to the next, that is CT. For this, we will multiply C into T to get Ct. Similarly multiply by T once more, we can get Ct square, and uh, we will take summation of all these values here for Ct and Ct square. After this, for the calculation of E, uh, first of all, I would like to tell what is E, and E is exit age distribution. It is the function that describes how long different fluid particles spend in a system before exiting. And to calculate this value, we will use this formula E equals to Ci upon summation of Ct. So for this value E, uh, here is C and summation of Ct is here. So this value upon this value, from here we can get E. So C upon summation of Ct gives E. Similarly, for all the rest of the readings, we can calculate the value of E. And for F, it is very simple to calculate F. And before this, F is cumulative exit age distribution. It represents the fraction of fluid particles that have exited a system by a given residence time, or showing how long particle is spent within the system is also this F. And to calculate F, just for first value of F, it is same as E, and for second value of F, we will add these two values of E. For third value of F, we will add the past values of it, that is these three values. Similarly for fourth, four values. For fifth, five values. Similarly for rest of the readings, we can get F. And moving to the next part, the, the first calculation is T bar, that is mean residence time. So mean residence time is the average time a fluid particle is spent inside a system before exiting, and the formula is summation of Ct upon summation of C. So summation of Ct is here. Summation of Ct is 6.367, and summation of C is 0.985. Here you can see. So by dividing these two values, we can calculate mean residence time. And after this, uh, this is sigma square, that is variance. Variance measure the spread of residence time around the mean. So for this, the formula of summation sigma square is summation Ct square upon summation of C minus mean residence time square of mean residence time. And from here, from these values, summation of Ct square on summation of C minus this mean residence time square of mean residence time will give sigma square, that is variance. This is sigma theta square, and for sigma theta square, we will divide variance by square of mean residence time. And after this d by ul is dispersion number, and it indicates the extent of mixing or deviation from ideal plug flow in a system. And it formula for dispersion number is sigma theta square upon 2. Just take half of the sigma theta square, we can get dispersion number. And this is the graph for C versus T, E versus T, and F versus T. Here, blue lines represent C versus T, red represent E versus T, F represent yellow represent F versus T. And the value of C, E, and F we already calculated here. C, E, and F versus this T. Okay, so this is the part. Now moving to the next. This is similarly the same procedure here for 20 lph. Here this is the volume of endpoints from burette we got during the experiment procedure. And similarly we will calculate C. CT, CT square, E and F from these formulas. N1V1 equals to N2V2. Here from this formula we can get C. For E we use this formula. For F we will use this formula. So similarly uh, we can get all the rest of the readings, and also the summation. Keep in mind to calculate the summation also for C, CT and CT square. Now for mean residence time, same formula we will use, and here we will take value from observation table for sigma CT upon sigma, sorry, summation of CT upon summation of C. And after this we will calculate variance, that is sigma square equals to summation of CT square upon summation of C minus square of mean residence time. And our third step will be to calculate sigma theta square, that is sigma square upon mean residence time, square of mean residence time. And the last part is to calculate dispersion number, that is again sigma theta square upon 2. So from here we can get the value of dispersion number, and by using these values C versus T, E versus T and F versus T graph will be plotted here. This is C versus T. Blue line represent C versus T. E red line represent E versus T, and yellow line represent F versus T. So this is the calculations and graphs for the RTD in PFR reactor. Thank you.
Okay, so now let's discuss about the results. So we investigated the flow characteristics of the reactor by analyzing the dispersion and the behavior of the system under different flow rates. So the key observations include: first, the graphical analysis. Uh, the graph of C versus T and E versus T and F versus T was plotted for flow rates of 10 lph and 20 lph. This graph illustrates the variation in concentration and flow behavior over time. Now secondly, calculated parameters, like using experimental observations, we calculated the dispersion number and dimensionless parameters for different flow rates for 10 lph and for 20 lph. So for 10 lph, the dispersion number value is 0.14055, and for 20 lph, the dispersion number value is 0.058242. Now let's come to the discussion. So from the experiment, we observed how the flow rate significantly impacts the dispersion characteristics and the mixing behavior with the reactor system. So the calculated dispersion numbers provide the critical insight into the nature of flow under different conditions. So first of all, let us see about the effect of the flow rate on dispersion. So like at the lower flow rate of 10 lph, the dispersion number was found to be 0.14059. This indicates higher axial mixing within the reactor. Such behavior characteristics of system transitioning toward mixed flow dynamics where dispersion dominates. Like at the higher flow rate of 20 lph, the dispersion number is reduced to 0.582, so suggesting a more plug flow like behavior. This is because higher flow rates reduce the time for axial mixing to occur, leading to more uniform flow. So now secondly, on comparing the reactor types, the experimental result confirmed the theoretical understanding of reactor behavior. In a plug flow reactor PFR, the contents move in a uniform manner with a minimal mixing, reflected by the lower dispersion number at higher flow rates. So conversely, in a continuous stir tank reactor CSTR, the contents are uniformly mixed, resulting in higher dispersion numbers as observed at the lower flow rate. And thirdly, the reactor behavior trends, like the transition from the higher value at 10 lph to lower at 20 lph, aligns with the expected trends of reduced axial dispersion at increased flow velocities. So this showcases the importance of flow rate in determining the reactor's behavior and efficiency. Next, the source of error and practical considerations.
like the presence of air packets in recirculation pipe, may have momentarily influence the flow characteristics as mentioned in precautions, allowing stabilization before measurements, helping mitigate the issue. So like minor fluctuations in flow rate or external disturbances could have contributed in the deviations. Now again in discussion, let us discuss some advantages as well as disadvantages. So beginning with some advantages. Firstly, for the low flow rate 10 lph, enhanced mixing. The higher dispersion number indicates thorough mixing, which is beneficial for reaction requiring uniform reactant concentrations or heat transfer. So suitable for slow reactions in process where reaction kinetics are slow. Increased mixing ensures better utilizations of reactants. Second, for higher flow rate of 20 lph, reducing back mixing, like the lower dispersion number mimics plug flow behavior, ideal for reaction with high conversion efficiency. Faster flow rates reduces the time requirement for processing, improving throughout. More predictable behavior, like plug flow like systems ensure predictable and consistent product quality, especially in large scale operations. Third, reactor type implications. CSTR provides continuous operation and uniform output, making it suitable for large scale steady state process. PFR for low dispersion numbers ensures high conversion per unit volume, particularly advantageous for competitive or sequential reactions. Now let us come towards some disadvantages. So like for a low flow rate of 10 lph, energy efficiency, high mixing can lead to higher energy consumption due to recirculation and stirring. Now for lower conversion, higher dispersion may cause back mixing, reducing the conversion efficiency of the reactor. Difficulty in scale up, like reactors requiring high dispersion are challenging to scale without maintaining uniform mixing. Now secondly, for a higher flow rate of 20 lph, potential maldistribution in cases of uneven flow, channeling or dead zones may occur, reducing reactor efficiency. Plug flow systems are less adaptable to field concentration fluctuations compared to fully mixed systems. Heat and mass transfer limitations, like limited mixing can restrict heat and mass transfer, affecting reaction rates. Thirdly, reactor type implications, like for CSTR, high energy demand for stirring and mixing, less efficient for reactions required high conversion. Now for PFR, sensitive to feed variability and challenging to maintain uniform conditions over large reactor lengths. So by understanding these advantages and disadvantages, we can select the optimal reactor design and operating conditions based on the specific needs of the process. Now let us come towards the conclusion. So the graph of the C versus T, E versus T, F versus T is plotted. It is observed that the flow rate decreases with time interval of 1 minute. So this finding emphasizes the role of flow rate in controlling dispersion within reactors and highlight the practical differences between PFR and CSTR systems. The experimental effectively demonstrates the relationship between flow dynamics and reactor design. So this focuses on interpreting results, linking them to the theoretical principles and addressing potential sources of error. Okay, so now let us have a look on some precautions that we followed during our experiment to ensure accurate results and safe operations. So first of all, addressing air packs in the recirculation pipe. Like during the experiment, we observed that air pack could form in the recirculation pipe from overhead tank. To mitigate this, we allowed the system to stabilize for some time before starting observation, and this precaution ensures a smooth and continuous flow without interruptions. Secondly, monitoring for overflows in overhead tank. Regular checks were performed on the overhead tank to detect any overflows. If an overflow was noticed, we immediately switched off the corresponding pump, adjusted the settings, and restarted the system. This practice helped prevent unnecessary spillage and ensured consistent flow rates. So again now on thirdly, like maintaining a constant flow. So to ensure the accuracy of the data, We kept a close watch on the flow rates. Any fluctuations were promptly adjusted using the actuator to maintain a constant flow. This step was critical for obtaining reliable results. Next, the general instruction for closing the experiment. After completing the experiment, we carefully followed the shutdown procedure. This included draining the reactor, closing the ball valves, switching off the pumps, and thoroughly washing the glass well. These steps ensured safety and prepared the equipment for subsequent use. So, following precautions, we were able to minimize errors and obtain consistent and reliable results. It is also highlighted the importance. It also highlighted the importance of system maintaining and monitoring during experiments. Thank you.